Thank you everyone for coming. So it's a great pleasure to introduce today's speaker, Mike Iacono. He is currently working at AER since 1987. He did his master's in atmospheric science from SUNY Albany, and as you all know that he is the principal developer of the RRTMG scheme, and he is here with us as part of a DTC visitor program. And he's working to develop a new cloud overlap scheme and trying to see whether it has an impact on tropical cyclone evolution with the HWRF model.
Okay, thank you.
Thank you.
Thank you, Bismas. Thank you, Lygia, for the opportunity to work with you here. I think it's been a productive collaboration that I hope we can continue. I'd like to thank my colleague at AER, John Henderson, who also contributed to the early stages of this project. So I thought I'd start off with a brief overview. First, I'll tell you a little bit about cloud overlap and what it is, and why this subgrid vertical correlation of fractional cloudiness is so critical to getting the radiation correctly. We're going to be comparing two different overlap methods within the RTMG code in HWRF. Maximum random method is the default, is already in the model, and we're going to be trying a variation of that called exponential overlap. After that, we'll talk a little bit about HWRF and how we set it up, and I'll tell you at this point that we are using the DTC trunk version of the code for the 2016 model as of early September. So all of the results you have seen are based on work that's been done just in the last month. And we've ran these three tropical cyclone cases that are listed here. So beyond that, we'll get into some diagnostics and verification. First, I'm going to show you a different way of looking at tropical cyclones. We're going to look at the long wave and short wave radiative heating rates within the storms. Now, this field is the primary way, along with the surface fluxes, that the radiation can influence the atmosphere and potentially influence tropical storms. So we want to demonstrate first that this change in the overlap is in fact changing the radiative heating rates. Beyond that, we'll show you some impacts on the temperature, moisture, and wind fields, and then we'll get into, toward the end, on the track and intensity verification for the cases we studied. So let's back up a little bit and talk about cloud overlap. The key feature to doing the cloud overlap in RTMG is McICA. This is the Monte-Carlo independent column approximation. This is a statistical method that's used for representing subgrid cloud variations. It's already in use in WRF and in HWRF, GFS, CSM, many other models. And this makes use of the G-point dimension in RTMG. And just to keep it simple here, I'll tell you that the G-points are quadrature points that are used to integrate PDFs of absorption to get the radiance in each spectral band and layer. So these are of length 140 in the long wave, and there are 112 G-points in the short wave. So what McICA does is it takes the scalar cloud fraction for that column you're working with, and it defines an array of the G-point length of values of 0 and 1 by randomly selecting zeros and ones to represent the cloud fraction. So for example, if the cloud fraction was 75%, it would randomly select about 3/4 of the G-points to be calculated as cloudy, and the rest of them would be processed as clear. So that might make you think that that wouldn't give you the right answer for a given calculation, because each G-point contributes differently to the final radiation. So randomly selecting some to be cloudy and some to be clear wouldn't necessarily give you the right answer. But remember, this is a statistical technique. So averaging over a larger sample or in a GCM over space and time has been proven to give you an unbiased answer and the right answer in the long term. So what this does do, it provides you the flexibility to correlate the cloudy G-points from one layer to the next. You now have this long array of zeros and ones. As you go from layer to layer, you have to decide how the cloudy G-points correlate with the layer above. And that's where the cloud overlap comes in. So there are several methods to define the cloud overlap. The default method is called maximum random. And in this method, all the continuous cloudy layers are forced to overlap as much as possible, or maximal overlap. And blocks of clouds that have clear layers between them are randomly correlated. They don't correlate with each other. So this is a rather severe approximation, as it's forcing the cloud to be maximally overlapped over its whole distance. There may be cases where you do have a tall cumulus cloud, but if you have wind shear, for example, it can be blowing the top of the cloud sideways relative to the bottom. The cloud won't necessarily be totally vertically correlated. It may be more randomly correlated the further up you go. So that's the rationale behind the other method that we call exponential random. And this is, it relaxes that maximum restriction within a tall block of cloudy layers by allowing the overlap to transition exponentially from maximum near the bottom to random near the top. Separate blocks of cloudy layers are still treated as random, but within a tall block of cloudy layers, it decays exponentially from maximum to random using a simple exponential I have on the screen here. So where dz is just the distance from one layer to the next, and z naught is called a decorrelation length. So the smaller dz is, or the closer the layers are together, the closer alpha will go to 1, or the larger z naught is, the more alpha will go to 1, and alpha 1 is maximum overlap. The larger dz is, or the greater spacing between the layers, or the smaller z naught is, that alpha will go towards 0, and that will be random overlap. So the z naught gives you a way to control the rate at which the exponential decays. And in this case, we're going to use a constant value. In the experiments we did, we used a value of 2 kilometers. And this, as I said, controls the rate at which the exponential decays. So to give you a single column example of the impact of changing the cloud overlap, these are flux and heating rate differences between exponential random and maximum random for 3 different cloud configurations where the clouds are indicated by the gray boxes. So on the left you have a low, shallow cloud, in the middle you have a taller cloud, and on the right you have a bisected 2 different cloud blocks. So the point here is that even changing only the cloud overlap by this simple method has pretty significant impacts on the fluxes, on the order of 10 or 20 watts per meter squared near the surface, and in the cooling rate on the order of a degree per day or more, just by this simple change. And that's a considerable difference, a considerable fraction of the total heating or cooling rate. So I'm going to mention here for completeness that there is another way to do the exponential random that we have not yet tested. And this is to use a variable value for this decorrelation length. It's otherwise the same as the previous method, but here the z naught is allowed to vary by latitude and day of the year. And this gives you a little more flexibility for defining where maximum would be used or where random would be used. So for example, you could use maximum more at low latitudes where you know you have taller convection and it would be more appropriate, where it would transition more to random at higher latitudes where random correlation is more appropriate. So I kind of like this idea. I think we will implement this in RRTMG, and we'll be testing that too in later experiments. So I'll get into now the details of our HWRF simulations. As I mentioned, we use the DTC trunk version as of early September. Lygia tells me that this is likely close to what they're using operationally at EMC, but there might be subtle differences if they made a few there. The model uses 3 nested grids with a grid spacing of 18, 6, and 2 kilometers in the inner grid. The 2 inner grids move with the storm. The outer grid is fixed, and it's initialized with GFS global model data. So we ran multiple 126-hour forecast cycles, each initialized at 6-hour intervals for each of the 3 tropical cyclone cases that we studied. So in each case, the first cycle was a cold start, so it's entirely dependent on the GFS initial conditions, whereas later cycles are what is called a warm start, where the atmospheric state from the previous cycle can feed into the next one, except for the vortex relocation that goes on to put the storm in the right place. And this ensures that the atmospheric changes that we see from the cloud overlap will carry over into the next cycle and won't be shut off by cold starting again each time, at least on the 2 inner grids. So here are the three cases that we studied. Joaquin, I'm sure you all remember, was an Atlantic case from about a year ago. It reached the Category 4 strength, had a very unusual track, moved southwest toward Bermuda, then turned around and moved out to sea to the northeast. The early predictions were very poor for both HWRF and for many models. Many of them were pulling the storm into the U.S., as you remember. Not very good forecast for one reason or another. So I picked this case intentionally, hoping that it might be somewhat sensitive to the radiation changes that we're testing here. So Dolores is an East Pacific case from July 2015. This also reached Category 4. This one was generally much better forecast by HWRF and other models, although the intensity was a little bit too weak. And finally, Gonzalo was an Atlantic case from about 2 years ago, also a Category 4 storm. And here the track also was generally well forecast, and this was a rather classic track of the storm skimming by the Caribbean and then turning northeastward out to sea. So I hope you'll indulge me here a little bit as I'm going to show you some diagnostics related to the radiative heating rates. So the idea here is to demonstrate that the cloud overlap change that we're making actually alters the heating rates to see if those actually impact the atmosphere. So we can also look at this and see if we see any details within the heating rate that tell us information about the inner structure of the tropical cyclone. So we're looking at snapshots in time so far, but I will be looking at spatial averages over time to determine whether any biases are present that persist long enough to change the environment and the evolution of the cyclone. So opportunities for verification of radiative heating rates with measurements are very sparse, as I'm sure you know, but I thought I'd mention here that the CloudSat instrument does provide a derived heating rate product along the satellite path through storms that just by chance happen to be sampled. So it's not a 3D product by any means. It's kind of hit or miss. If the satellite happened to pass over a storm, then they will derive a vertical slice of the heating rates through the particular storm. And this is just an example I have here from Hurricane Julia from 2010 that show you the long wave heating in red and long wave cooling in blue near the tops of the high clouds. So that's a diagnostic that conceivably we could use in the future. So let's look at some of our own results. These are now long wave heating rates for Joaquin. This is now a horizontal map at 900 millibars for the maximum random on the left and the exponential random on the right. This is for a particular time, October 2nd, 2015 at 12 UTC. So the scale goes from plus or minus 3 degrees per day here, where the red is long wave heating, and this represents very dense clouds which are highly absorbing and emitting irradiation back down to the surface. And the blue and purple areas are where you have long wave cooling, as you would expect in an ordinary clear sky. So those are the relatively clear areas of the scene here. So although the overall structure is very similar, we do see significant differences even at this stage in this cycle, especially in this area toward the south of the eye is providing much more heating rate in the ER case and somewhat less cooling along the western side of the storm here. So let's take a step toward the CloudSat product, and I'll show you a few vertical slices from our results. Thought first I would show you a more tranquil tropical sky. This is an east-west vertical slice through a relatively clear part of the grid, where you see cooling rate through most of the scene here in the blues and purples. And then the spots of orange and red are where there are a few cumulus clouds that are absorbing radiation and emitting it back to the surface. So I'm going to switch you now to a slice through the middle of a Hurricane Joaquin, and that looks like this. So here we see the clear sky in the eye is pretty apparent. That's the blue and purples there. And the eye wall is the very dark areas near the surface on either side of the eye. And in the outer parts of the storm, we still have clear air aloft. But all along the lower and mid levels, we have convection, as you can see here in these dark red areas. So there are considerable differences between the two. If you look at the details, over here in the ER case, we have clouds that are pushing upward into the clear air that are not apparent in the MR case in this case. And maybe it's my imagination, but I see the eye wall leaning outward a little bit, as if the convection were slanted, as you might expect in very strong convection.
What's the vertical resolution that you're using?
We have a question in the audience about what the vertical resolution is. I believe it's 59 layers.
61.
61 layers, Ms. says. The ice freezing level is this line right through the middle of the scene here. So above that we have ice operating, and below that liquid. So you may be asking here what the cloud fraction looks like at this time. So I'm going to replace the bottom panel with the cloud fraction, and that looks like this. So the dark magenta color is where it is completely overcast, high cirrus clouds, and of course in the eye wall here. And below that is where we have the partial cloudiness. And I should reinforce that this overlap change only operates when you have fractional cloudiness. It's ineffective where you have overcast because the clouds are already overlapping completely. Okay. So again, we see that the convection is slanting outward a little bit. So let's move northward about 20 kilometers and take a slice through the northern eye wall of Joaquin at this time. And that looks like this. So here you see the full breadth of the eye wall where all the action is going on. Those are the very dense clouds in the eye, absorbing and re-emitting long-wave radiation back to the surface. And yet, near the top of the eye, it's still relatively clear. So this gives us a sign that the eye is wider at the top than it is at the bottom, which is not unusual for very strong hurricanes. And so, again, we do see small details of differences between the two that suggest we are changing the environment. I have one more heating rate plot for you, and that is a shortwave heating rate. This is back to a horizontal map at 900 millibars for the same time as the long-wave map I showed you before. Kind of a funky scale, but I wanted to pull out the detail here. The blues are where you have relatively little shortwave heating, because that is where it's underneath the very dense clouds, so there's much less shortwave energy getting underneath the cloud to provide any heating, whereas the dark red areas are where you have partial cloudiness or clear skies, and you have stronger shortwave heating in that column at this level. So here too we see pretty substantial differences between the two cases, which with much more dense cloudiness and lower heating rates along the eastern part of the storm here, and in part of the spiral band we see more cloudiness going on. So these are indications that we are having significant effects on the heating rates that in turn have a good chance to affect the environment of the storm. All right, so let's get into some more traditional gridded atmospheric fields and see how those are changing. So at this point in the project, we've only examined model-to-model differences between the exponential random and the maximum random to show the sensitivity of the atmospheric state to these changes in the cloud overlap and the heating rates. So we will do a verification with GFS analysis, so that's in progress at the moment. I didn't have enough to show you today, but we will work on that next. So these are data that have been converted to the regular grid, and I'll be showing you maps of temperature, specific humidity, and wind speed at different levels. We have a question, yeah?
What you're showing us, differences between individual runs or some ensemble?
We did do multiple cycles, but for the moment I'm showing you results from an individual cycle. I'm not yet averaging over cycles. Though I do some time averages here, which I'll show you in a minute. So this is for an instant in time, the 850 millibar temperature for a somewhat larger area than we were just looking at. You can't quite see it on these maps, but the east coast of the U.S. is in the western part of this figure, and the northern Caribbean is in the south lower left corner. Oh, sorry. So there's about a 2,000 kilometer area we're looking at it, and of course the storm is right in the center. So what I have plotted on the right is the difference between the two experiments to make it easier to see where the differences are. And at least at this time, we do see pretty substantial differences in temperature at 850 millibars. And I'll point out to you that the difference scale is plus or minus 5 degrees, so these are not minor changes. In addition to this big area of warmer temperatures that's really over the continental U.S., there are patchy areas of warmer and cooler areas, including right in the center of the storm. So to get a different view, I've also averaged these over multiple days. So this is a 3-day average over the same scene I showed you before. And of course it smooths out the temperatures on the left. But of relevance on the right is that now we do see these warmer temperatures persisting over a much longer time period. So that's an indication that we are now changing the environment considerably, not only near the storm, but in the surrounding environment that, as you all know, can influence the storm's future track and intensity. And so we're seeing cooler temperatures here very close to and to the south of the storm. So let's move on to specific humidity, also at 850 millibars. So on the left is the actual specific humidity field, and of course the highest values here up to 18 or 19 grams per kilogram are right in the center of the storm. And not surprisingly, we have bands of somewhat higher moisture feeding into the storm. It's not unusual for a storm of this size. And on the right, I'm showing that we do see, again, pretty substantial differences in specific humidity at this level. And the scale is about plus or minus 8 grams per kilogram out of 18 or 19. So again, these are pretty substantial movements or advections of water just caused by this simple change in the cloud overlap as it's allowed to evolve. This is about 5 days into this particular cycle, so it's had time to evolve and change the atmosphere somewhat. So I've also done a 3-day mean of this, and this also shows that these differences are not washing out. They're persisting in time in different areas. So this is a sign that these changes will have bigger effects on the surrounding environment, in moisture as well.
Question. So, like these 3-day mean plots that you have, is that done kind of in a vortex following framework, or is it just locked in place? Because it seems like the path of the TC should be more of a track if you're averaging over 3 days.
That's a very good question, and this is storm-centric, but it was already done for me because these are data based on the inner grid, which is follow the storm. So the storm was centered in each of the areas that I averaged. In this case,
D02 domain?
I think this is a 3.
3?
Yeah. Maybe it's a combination of them.
Yeah.
I think it's a combination of them.
So then the geographic outline wouldn't apply to all the.
I suspect that's true. Yeah, I suspect that the outline may not be in the precise place because of that averaging. Okay, and so let's look at wind speed, and this one turned out to be fairly interesting at 200 millibars. So on the left is the actual wind speed at 200 millibars for the maximum random case, and as you can see, there's essentially no steering currents around the storm at this time, very low wind speeds over the ocean, but there were very high wind speeds over the U.S. at this time. And although the direction isn't represented here, I can tell you that these are all roughly southerly winds over the U.S. at this time. So when we look at the difference, we see something very interesting, and that reminding you that the storm is right there, that in the eastern, northeastern, and southeastern quadrants provide much higher winds, but in the western quadrants we're getting much slower winds. So to me, this means that either these strong winds over the continent were either weaker or were further west in the exponential random case than they were in the MR overlap case. So this is starting to give us some evidence that we're starting to change the circulation pattern that can influence the track of the storm. Sure.
So if we are doing the averaging on a storm-centric way, and the tracks are different in the two simulations, we're going to be averaging things that are in different geographical locations. So when we look at the environmental winds, that could be due to two factors, right? The influence of this change in the radiation, or just the fact that we are in a different place on Earth. Is that?
It is possible that the two grids between MR overlap and ER overlap are slightly shifted if the storms were in slightly different places. For the time period I'm looking at, they were not especially different.
Okay.
Okay. But that is a good point. So this does lead into the next set of plots, which will show us the verification of the track and the intensity for a couple of cycles. So these are for two cycles initialized at slightly different times. Now in these, excuse me, in these plots, the white is the verification where the storm actually was. And we're showing three model results in these plots. The 2015 model result, which was just archived, we did not run that, is in green. And the result of our two experiments for the MR overlap is in blue, and for the ER overlap is in red. So at least for the case on the right, we see where the model last year went up the coast during this cycle, and our experiment with the MR overlap ran up the coast, where the track with the ER overlap followed the others for a while, and then as the atmosphere started to evolve, it got held back. Now, is this a result of a change in the winds over the continent? I can't really prove that yet, but there's evidence to suggest that might be contributing, that it didn't have strong enough winds to be pulled up the coast as they were in the other cases. And something similar happened in the cycle that was initialized 12 hours later, where the tracks all followed each other for a while and then started to diverge, with the two experiments that we ran being closer together at this point, but still varying by a couple of hundred kilometers at the end of the cycle. Now, neither of these is a perfect answer, obviously, but it's showing that we're substantially changing the environment and the track of the storm. So at least it's a change in the right direction. So these are tracks for two subsequent cycles, and we see similar behavior. In this one, the two storms tracked each other for a while, and then the MR overlap case decided to go northward, where the ER overlap swung around and then came back along the path that the storm ultimately took toward Bermuda. And in the final one, the two models are essentially in better agreement, finally. Though not quite in agreement with the observation, obviously. So it's a sign that maybe we're changing things in the right direction, but obviously there's still things to understand about why it's not right yet. As for intensity for Joaquin, this is now a plot of time versus pressure. This is the central pressure intensity. So again, the white symbols here is the observed intensity for the storm over this period, and the colors are the intensity for all 9 of the cycles that we ran for each case, which are each initialized at 6-hour intervals, so they're all starting at different times here. So we have MR overlap set on the left and the ER overlap set on the right. So we can look at these and see that some of them are a little bit better. I think the one in cyan is a little bit better in the ER overlap. Maybe the one in magenta and the purple one looks a little bit better, while the yellow case is clearly worse in the ER overlap. So it's kind of a wash. We get some cases that look better in intensity, some are a little bit worse. But we're not making things drastically worse, which is a very good sign. So let's take a look at Dolores. This is a case that was much better forecast to begin with, and we're really not changing things substantially here. In both of these cycles, these are 2 different cycles, we pretty much follow along the observed path as was done in last year's model. except for the end of these cycle where it starts to vary off a little bit for a reason to be determined. So the intensity for Dolores looks like this, and we didn't run as many cycles for this case, but we have 3 or 4, and they're fairly similar. The first 2 cycles, the ER overlap is a little bit weaker. We don't know why yet. The red cycle was missing from this case. That file got corrupted. I didn't leave it out because it was a bad result. I just couldn't plot it for you here. And the yellow cycle was intensified much stronger than the observed storm, and then stayed steady after that. So in that cycle, we're doing similar in the 2 cases. And finally, for Gonzalo, this storm was also forecast relatively well, and we don't make substantial changes here in the cycle on the left, though there are subtle adjustments to the track in the cycle on the right, on the order of 100 kilometers. And for Gonzalo intensity, here we only ran 2 cycles, and in both of these, their blue cycle is fairly similar on intensity, but the green one is a little bit weaker. So that's kind of a trend we're seeing, that maybe we're weakening the storm a little bit too much. But you have to keep in mind that you can't really look at the intensity separately from the track. You may be getting a different intensity because you're putting the storm in a different location. You're putting it in a different environment. So it may be weaker just for that reason. So you really have to look at these 2 in combination. All right, by way of summary, I can tell you that we've examined the impact of replacing the MR overlap with the ER method for several tropical cyclone cases. We've shown you that the long-wave and short-wave radiative heating rates are substantially altered simply by changing the cloud overlap method in this one way. We've also shown you that subsequently changes the temperature, moisture, and the wind speed, not only within the tropical cyclone, but in the surrounding environment. And thus, we're setting the stage for moving the track around, at least in some circumstances. And Joaquin was one of those cases where the track was significantly altered simply by changing the overlap method, with some intensity changes as it varied by cycle, with much less of an impact in Dolores and Gonzalo, which were forecast well to begin with. So for future work, I'd like to test this alternate ER cloud overlap method with the spatially variable decorrelation length. Since we know we're altering the environment around the cyclone, it might be more appropriate to use this other method. I'd also like to take a shot at using some of the CloudSat heating rate products for verification of the heating rates we're calculating, at least for storms where their product is available. We will be working on verifying some of these atmospheric state changes with the GFS analysis. And finally, I'd like to suggest that running cases for Hurricane Matthew might be interesting, since that case was obviously very difficult for many of the models to predict. So I think it'll be an interesting case to study in this context as well. So that's all I have. If you have any questions, I'd be happy to answer them for you. Thank you. There's one over there.
Questions, please.
So when looking at the cloud overlap methods and the intensity forecast in the different cycles, how do they compare to, I guess, the original HWRF forecasts for those cycles?
That I do not have here. So I can't answer that. I didn't look at the last year's model you're talking about.
Yeah, I guess just what the baseline against which you're comparing to say that, these methods reduce the intensity. It's like, well, reduce the intensity. Do we know that it reduced the intensity compared to not using these methods? Or
Well, as we said, we think the 2016 model with the maximum random overlap runs that we did are very similar to the operational code. There may be subtle differences, but in this case, that's the reference that I'm using.
Okay.
have you tried this in any other NWP application?
Changing the overlap?
Yeah, or is this the first attempt?
I have not myself, but other people are using it in their GCM applications. We know that the NASA GEOS model is using this exponential random overlap that uses the correlation length that varies spatially. I don't have details on what their experience has been with that, but we can contact them and interact with them.
So a follow-up question, and you and I talked a little bit about this, was about the potential need to make the scale, to make the correlation scale aware. So if someone is running this partial cloudiness radiation interaction in a GCM versus in a high-resolution NWP model, say with the HWRF with the grid spacing down to 2 kilometers in the inner nest, should the treatment of the overlaps be different? Because if you have a pretty large grid, maybe you can expect that less vertical correlation.
Yeah, I think that's a very good point. We are down to 2 kilometers here, so we're getting close to the scale where we may be resolving the clouds. So I think that's a very good point, and we should take that into consideration. Behind you, Biswas.
I was just wondering if you had a sense for why Joaquin seemed to be more sensitive to changes in the cloud scheme. Is there a difference in total cloudiness or amount of subgrid cloud in that
That
storm?
was just a random guess on my part, that the storm was not forecast very well originally, suggesting that the environments were not being modeled very consistently among the models, and so that there would be a sensitivity to this kind of change. And as it happened, it turned out that way. Could be just a coincidence, but I suspect, based on the experience here, that this change will affect some storms more than others. And we can only learn that from studying a larger set of cases.
Any other questions? Why not?
So my kind of thought on Joaquin is that it's like a bifurcation. So it would be interesting to, as a baseline predictability experiment, to randomly perturb the grid, see what the tracks do, and then you could kind of try and start to infer if scheme changes have physical improvements, or actually like physically have physical reasons for improving the track, rather than just say, oh, I perturbed my grid and I got a forecast that looks more realistic. It might be an interesting experiment to
No,
to
that's
try and
definitely an important thing to do, to try to piece together why these things are happening so that we understand the physics behind it and can actually improve the models and know that we're improving them the right way for the right reason.
Yeah.
So this technique is only as good as the partial cloud that is passed into the RRTMG.
That's very true, yes.
And it seems that there is still a lot of uncertainty on that part, right? You talked a little bit about a possible method or observational data set to evaluate that. Can you talk more about that?
About the cloud fraction?
Yes.
I'm
just wondering how we can evaluate this, and if there is a way to tease out, like what's the error due to one part versus the other.
Yeah, I agree with you that there are very big errors in the cloud fraction in these models, because it's a fairly simplistic way in which they're parameterized. Some of the simpler ones just give you binary clouds, and so changing, that is clear or overcast, and so changing the overlap really wouldn't have had any effect. So in this case, we used a variation of the clouds that parameterized that Greg Thompson developed to provide somewhat more fractional cloudiness throughout the layer, throughout the whole scene, and that gave us the opportunity to impacting the environment. Greg has done a lot of analysis of what he's done, and he's showing that it's providing a better result for cloud fraction But I agree with you that verifying those is critical and needs a lot of work.
So, HWRF is run with the Ferrier-Rayleigh group microphysics. Do you think that using other microphysics like Thomson microphysics may improve the skills of the cloud overlap method?
Not something I can speculate on really without doing the runs.
Yeah.
It's certainly possible.
Any other questions? Okay, just thank Mike again.